start out with any questions?
The bulb, rock or whatever, the bulb you can turn up at the end, coming back down. The ground was, what we decided was zero.
Yes.
Okay, there it is.
We in that royal sense. I decided, I forced that upon you.
Yeah,
Well,
yeah. We decided where zero is, which way is positive, which way is negative.
yes.
Maybe we should.
Yeah, so whenever you work in a problem, you know, we potentially could all choose a different direction. Well, in a one-dimensional problem, either left or right or up or down, or, so half of us could choose one way, the other half could choose the other way.
Well, when you're dealing with gravity,
There are some logical ways, but.
we know the pole is to the center of the earth, so.
But when we get into the force problems, it usually makes sense to make one of the positive directions the direction of acceleration. But sometimes, if an object's moving opposite the direction of acceleration, sometimes it's more convenient to make the direction of initial movement to be positive instead of necessarily the direction of acceleration. It depends upon your mood at the time.
Or what's gonna make the problem flow easier?
Ultimately.
Yeah.
Any other questions? I know everyone's anxious to derive the rest of those formulas. All right, it's been a week, let's do it. All right, so we derived that one. Quick refreshers here. So I have a position time graph, and we'll make it a straight line. I take 2 points. This would be the change in position, and this would be the change in time. And so my slope, which is change in position over change in time, also happens to match velocity. So that we've hit before, it's not new there. By the same token, if I have velocity versus time, let's make that a straight line. Take 2 points. I have some change in velocity here, I have some change in time, and so my slope, rise over run, is acceleration. So if I take the slope, I get the next one down. So from position versus time, I get velocity. From velocity, I get acceleration. And let's just do a quick trivia here. Change in acceleration over change in time. SI units would be meters per second cubed. I'll stick with just the US version of it. I was looking up, there's some other countries sometimes use different words for this next one. Oh, there it is, okay. So imagine that you're at so we'll talk about change in acceleration. So you're sitting at a stoplight and the light changes to green. So you slam your foot down on the gas pedal and you take off. So you're going this way right here, this is your head, this is your body. You get this supported right here. And when you slam your foot onto the gas pedal, what happens to your head?
Shoves back.
It goes back because it was
not moving and suddenly it's moving.
Okay, and then I was looking for a specific word, Brian?
If was forced back because it had no
Oh,
support.
I thought you said something else.
Okay.
I thought you said jerks back.
The velocity of your head was at 0 and now it's moving.
Well,
Yeah, it would be, I mean, there's that inertia thing, your head wants, your whole body wants to stay still, but the force is right here. But your head basically jerks back, and so change in acceleration over the change in time is jerk.
Is that like an actual term that we're?
I have seen it in 2 books, it has been in a couple of referee journal articles. Jerk is not internationally accepted, it is US accepted. Other words, sometimes you'll have jolt, surge, and lurch are the other ones that it's sometimes called. Position, velocity, acceleration are international. Jerk has not gotten the official seal of approval, but among physicists, if you talk about the jerk within the context of motion, they'll know what you're talking about. And then, the change in jerk over the change in time. So you slam your foot on the gas pedal to take off, suddenly you realize the car in front of you is not moving, and so your head basically does this maneuver when you slam on the brakes. What's that called?
Whip.
It would have been nice if they'd come up with that one, they did not.
Okay.
Rebound. I don't know.
Snap.
of course.
Snap actually has been in 2 referee journals. Getting into a referee journal, that means that basically when a physicist wants to publish, a referee journal is one where they send it to the publisher, who then send it out to other people in that specialty, who will then review it, give feedback, and then there's this iterative process until everyone's happy. But Snap has actually made it into a referee journal, and I don't know what the symbol for it is. Generally, at some point, typically in physics, they sometimes do the dot notation. They put a little dot over it, and then this would be 2 dots, or V with 1 dot. For those who've had calculus, this represents the derivative with respect to time, specifically time. And so this would be X, triple dot, and so on. Now, most of you, although if I just said right now what's the change in snap or the change in time, I think most people probably would draw a blank. However, most of you know what comes after the word snap,
Crackle.
and then, yep. And so change in snap over change in time is crackle. And then pop.
Is this for real?
Yeah.
Okay.
Again, once you get past acceleration, the question is it internationally accepted or not? Jerk, I've seen in books, snap, crackle, and pop have shown up in print as part of legitimate physics. However, it's not internationally accepted yet. However, I think most physicists, if you talk about the snap, crackle, and pop of it, they'll know what you're talking about.
Okay.
All right, so let's work backwards. Let's just start out with a simple velocity time graph. I think velocity time, and let's assume that the velocity is constant. Let's throw numbers into this. Let's make this 50 meters per second. From time 0 to time 6 seconds. What's the area?
300 meters per second squared.
Ooh, nope.
Where do we see? Oh, what is that? 50 times 6? 50.
Yep.
Yeah.
I'm not questioning your math. Just the units where you.
Yeah, I saw that figured.
Let's work it out.
Yeah.
What do you do to find the area?
Length times width.
All right, so the area here, 50 meters per second times 6 seconds. So the math part, 300, no problem there. but units,
Just meters.
just meters.
Yeah.
So there's some indication that the area here has something to do with displacement or position. And in fact, it does deal with displacement. Say again?
Antiderivative?
Absolutely. Or for those who've gotten to Calc 2 or far enough into it, integrals.
What- Excuse me, what's that symbol after crack? Is that 6?
This right here, that's an LE,
LE,
that's a crack.
Crackle.
LE. There you go.
So we can generalize this, that the area under the velocity versus time graph is equal to the change in position. This won't tell us actually position. All I know is I've gone 300 meters in the positive direction. Yep, right.
I was just gonna ask, when are we gonna see a graph like that? I guess when,
The linear motion lab, but I think it's also something like that.
yeah, there was, okay, never mind.
This would be a graph similar, that could potentially correspond with a position time graph or something like this.
Yeah, it makes sense, like if a word problem's like, an object is moving at 50 meters per second over, yeah. Makes sense.
Although we'll typically have acceleration involved. Alright, so now let's take a look at this. I have some initial velocity here. I have a final velocity here. I know final velocity is equal to the initial velocity plus acceleration times time. So this also equals initial velocity plus acceleration times time. And I know acceleration is just my slope. So my area here, and we can go for the stunning visual effects, I hope. Ooh. I basically have a trapezoid. I got the parallel sides here, and I have non-parallel sides over there. I'm gonna find the area just by looking at the rectangle, basically finding this rectangle here, and then finding the area of the triangle. And so my area, my displacement, is equal to, make that some time t, the area of the rectangle, which is VI times t, that's height times width, plus the area of the triangle,
1/2 base times height, except that's like really basic. So like 1/2, velocity final times time, like times time.
not velocity final, because the triangle goes from here to here.
Right. But wouldn't velocity final be the velocity minus velocity initial? And that would.
Wait, say that again?
So you've got your velocity on your y-axis. If you
Right.
subtracted velocity initial, like VI,
Right.
then that would give you that.
Okay, so V final minus V initial, which is
Oh,
just AT.
Yeah, okay, it's not, yeah. I said it wrong, but the idea was right.
Okay. All right, so we have a formula here for displacement. Cleaning up a little bit, VIT plus 1/2 AT squared. And that's the second K formula. At least the second one I'm deriving right now. I guess I used X over there and I'm using S over here. Again, S is more generic than X is. I'll flip back and forth between using S for position and X for position. Does anyone care? Which letter I use?
Can we just keep it X? If that's okay, yeah.
Alright, delta X equals VIT plus 1/2 AT squared. convoluted way of doing the next bit, but. Oh, let's go for it. So what I'm gonna do is I'm gonna take this acceleration here and solve for it, and then plug it into the second equation. So, or go back to acceleration is v final minus v initial, divided by however much time took place. Delta t formally, but I don't feel like writing a delta right there. I'm gonna plug that into here. So I have, this is VIT plus 1/2 times V final minus V initial over time, times time squared. Dramatic pause for people to catch up in writing and for to ask questions about what I just did. That time cancels out with one of those times. And so I'm left with VIT plus 1/2 VF T minus 1/2 VI T. Distributing the 1/2 and the time. And so I have a VIT here and a 1/2 VIT there, which I'm subtracting, so I end up with 1/2 VIT plus 1/2 VFT. I'm gonna factor, so I'm left with 1/2 VI plus VF times time. And that's equal to my displacement. Again, we are assuming acceleration is constant. All right. Let's take a look at this graph again. Write it up. Velocity, time. Acceleration is constant, so it is a straight line. VI. Recognize what we have here in the first part, this right here, the 1/2 VI plus VF. That's just an average of two numbers. Brooke?
I'm backtracking a bit, so this 1/2 VI plus VFT, that's just, the other formula rewritten. the,
That's
like-
this one right here where I factored the 1/2 out and I factored time out.
Okay, and is that the same as the like VIT plus 1/2 acceleration T squared?
That's where I started, and then I solved for acceleration in the first equation,
Yeah.
plugged it into the second.
Okay, so they're the same, it's just written differently.
Yeah, this is a combination of those two.
Okay,
Although usually, if you look at the old videos or probably the hand and paper videos, I generally start with these two and derive that one from it, but. Did I answer your question?
yeah.
Okay. Other questions at this point? So the 1/2 VI plus VF is that's just a number halfway in between, it's the average of those two. That's this point right here. What we're saying is that the area underneath the trapezoid is equal to the area in pink right here, where this is just my average velocity.
And is that a cake formula?
This is the actual cake formula right here, but I think the textbook writes it slightly differently.
They put it over two, they distribute that half the rest of the way.
Maybe it's a different textbook that writes it slightly differently. So the cake formula, delta x, is equal to VI plus VF over 2 times time. Or sometimes they will do delta x is equal to the average velocity times time, where the average velocity is just VI plus VL. Those two. But we have three of the cake formulas. One more to go. That dramatic pause was for questions.
So which formula is actually your third big formula? Is it the,
This one.
that one?
Well, so you were saying that the one that you have circled is a combination of the two that are on the top left?
If I take these two right here, I can combine them to produce this.
So we have the three that are up there and that fourth one that's circled?
Well, these two are the same. Here I'm multiplying by half and here I'm dividing by 2.
Alright.
These are not independent of each other, they're all interrelated.
So all of the cake, equations are like just the same, but just written in different ways?
Yes, and there's a reason for that, which we'll get to. Hopefully it will save you time. Or you could just drive it all from scratch every single time, but not the most efficient use. All right, so the last one, let's talk about dot products. Because we've talked about adding vectors, and subtracting is just adding a negative, and a negative vector just is the other way. But we haven't really talked about multiplying.